Hi guys, can I get a sound check?
Hello, you're good.
Okay, great, thanks. Where were we? Let's see. Hey guys, I had a sort of a question for you guys. So if you wanted to get advice or hear more about some aspect of what to expect at work when you go into industry, et cetera, or whatever, do you guys have any particular things you'd like to hear about? Um, just trying to figure out where to, I always, like I was mentioning to you guys, I always sort of have this sort of a non-technical part of the class where we talk about different things. Maybe it's stock options, maybe it's looking into companies reports or figuring out where you fit in the overall scheme. any any Anything you guys want to ask for? Any requests?
Yeah, I have a couple things I wouldn't mind asking for.
Okay.
Sure, I'm actually pretty interested in your entrepreneurial history.
Uh-huh.
So anything along the lines of, especially early stage startups, funding routes, do you go angel investor, VC, that kind of stuff, accelerators, all that stuff. I mean, in particular the early stages, kind of what your experience is in that realm, particularly to just the technology.
Okay, great. I'd be happy to do that. And I think I have a reasonable amount to talk about there. So I worked for two other startups, which were good. One of them was very highly VC venture capital funded. The other one was a bootstrap. Our own company that we just recently sold was self-funded, and it had funding from key customers. So those are some of the examples. I'm trying to put a company together now, sort of self-funded, so that we can talk about that. And I just happened to have, I just at the beginning of the year, I joined a angel investment group in, just happens to be in San Diego, but I guess it would be anywhere. So I'm sort of like part of basically that group, and I'm kind of seeing the pitches from various startups, and the internal discussions about whether to fund them, how much, valuations, of stuff like that. So I think from drawing from those, I think I can bring something interesting for you guys to talk about that.
Yeah,
So
that'd be great. That's perfect. Thank you.
okay, sure. Yeah, I'll put some stuff together. Maybe every week or something, we can spend 10, 15 minutes talking about that. Okay, great.
Thanks, President.
Sure. That sounds like a lot of fun. So I'll do that, and hopefully you guys will get something out of it, and hopefully it'll get your entrepreneurial juices flowing. So great. Thanks for the suggestion. Who was it that suggested it? Just so I can know.
That's me, Raymond Deals.
Okay, great. Thanks.
Thank you.
Okay, guys. So now jumping into back into our sort of course overview. We were talking about this business of the robustness of a gate to noise, and we define things like noise margin, and these properties of suppressing noise and increasing the signal. Now let's look at what an ideal logic gate would look like, an ideal inverter. So this is an ideal inverter. Again, what an inverter looks like is sort of logically, schematically looks like this. Okay, it has an in and an out. So if you just think of it as a logic element, when in is 0, out ends up being 1, and when in is 1, out is 0. Okay, so when you reduce this or make this from a circuit element, make this logic element, there's no real ones and zeros in a logic element. You have to have a voltage that represents 0 and a voltage that represents 1, because we're in a real circuit where we don't have zeros and ones that are that are unitless. So let's say we call 0, we define that as 0 volts, and we define 1 as the supply voltage. Okay, what's the supply voltage? Well, depending on the CMOS process technology you're in, it could be, for really old processes, maybe supply voltage was 3.3 volts. For, the newest stuff, it could be 1 volt or 0.9 volt. In this class, we'll deal a lot, in the labs. The process we're looking at is a sort of a older process, and we're going to be playing with a TSMC, that's the manufacturing company, 0.8 micron process, and that'll have a supply voltage of 1.8 volts. So a 1 would be, 1.8 volts or something like that. So in that case, in that particular case, you would have something like this in the real circuit. You'll have 0 volts, might give you a 1.8 volts on the output. What you'd like to have that. Because your supply voltage is 1.8, you're certainly not going to do any better than that. So if you have an ideal logic gate, the most they can supply is this 1.8 volts. Okay, and then if you have 1.8 volts, you'll have 0 volts on the output. So again, those are the two supplies, two extremes of voltages available in your circuit. So if you have, 0, you can't go any below 0. Again, assuming you don't have negative voltages, you typically don't have both negative and positive voltages in a logic circuit for the most part. So if you look at the extremes of voltages that are available to you, on one end you have 0 volts, and on the high end you have the supply voltage. So just let me call it the supply voltage. So one question would be, well, why don't we assign the logic 0 to something in between? Or why don't we assign the logic high to something in between? Well, it just comes out of the fact that we want as much to get this high noise margin, to get a lot of reliability. We want our logic 0 and logic 1 to be as separated from each other as possible. So if there's noise, system noise in either one of those, they still don't get confused for each other. Okay, so we want them to be as far apart as possible. So that's as efficient. You can't get any more efficient than using your highest value, which is the supply voltage, and your lowest value, which is ground. So that's the idea here. So if you look at an ideal gate, okay, your input, so this is, again, this is a transfer function for an inverter. When the input is low, your output is high, and so it'd be this case. And when your input is high, your output is low here, so it'd be end up here. Okay, so those are either ends. And in a ideal situation, this would be the supply voltage, because you're not going to do any better than that. And this is also going to be the supply voltage. You can't do any better than that. And this will be ground. Okay, so in low, out high, in high, out low, and then at some point there's got to be a transition between them. Okay, so here let's talk about why this particular this rectangle thing is an ideal logic gate. Well, one nice thing here is that in this region and this region, your resistance is no, let me take a step back. So one thing is you want it to have a, well, no, sorry guys, I'm trying to decide which one to talk about first. So let's talk about this first. What you like about this region and this region, you do not want to, let's say there's noise on the input. Noise on the input is going to look like something like this. This is the input axis. If I would make this sort of time out here, you'll get a bunch of noise here. As long as that noise is low enough, this guy will just give the same output value, high output value, the whole time. So it's basically, as long as it's in this region, it's completely rejecting the noise. It's always outputting the supply voltage. Okay, when it's here also, you want this transfer function when, if there is noise on the input, the output is always giving you, completely rejecting that noise and giving you an output 0. Okay, the only time the circuit is going to get confused is if your input, for whatever reason, is sitting here in the middle and is noisy. Okay, then because it has infinite gain, this straight line, so remember gain is defined as V out. The gain of a circuit is defined as V out, change in output voltage with respect to input voltage. And if that's a straight up and down line, means the gain is infinite at that point. So if you have any noise here, the output is gonna just be chugging between 1 and 0. So the only point where you won't be rejecting the noise is if you're sitting there right in the middle. Okay, so you want a very flat curve here, very flat curve here, and you want a very abrupt curve here, up and down. So flat here, and very abrupt transition here. Okay, and to have, so this is kind of your noise margin low. This is your noise margin high. And if you want those two, the noise margin high and low, to be, usually, you don't know if you're going to get more noise on the supply or the ground. So you like to put it right in the middle. So ideally, this would be at the supply voltage divided by 2. Okay, so you'll have this very flat response, very flat response, very abrupt response, and you want to put this placed right at the middle of the supply. Again, you're dividing your noise margin equally in the noise margin of a high value and a noise margin of a low value. Okay, so those are ideal things. On top of that, you'd like a few other things. So we defined fan out earlier as the ability for a gate to drive a bunch of gates like itself. That's a definition of a fan out. But anytime you're talking about driving multiple other gates, we're calling it fan out. That's typically a lot more, you see that more than fan in, but let's talk about fan out for now. So, when you're designing logic circuits, it's very, very typical for one logic gate to drive a bunch of other logic gates. You certainly don't want to limit yourself. So basically, you'd like to have a situation where you can drive as many other gates as you need to, okay, as you want to. So you want the fan out ideally to be infinite, meaning that this one gate can drive as many other gates as you like, and you don't have to think about it. You don't have to worry about how many do you have, okay? You want the input resistance to be infinite. Why is that? So basically, if I have a logic gate here, I want the input resistance to be 0. Why is that? Is because you could end up having a voltage divider action. Imagine I'm driving this logic gate with a source, and think about that voltage source. As voltage source typically do, it has a series resistance. Okay, now imagine if I'm driving the gate with that, and the gate has sort of a input resistance. So this, what it's going to look like is the source is going to be, so Rn, you're going to end up having a voltage divider situation here. Okay, so the V in actual is going to be the input resistance of your logic gate divided by the input resistance of the logic gate plus the source resistance. Okay, so basically, if you have an input resistance, if you have an infinite input resistance, these things cancel each other out, and you end up with just having a that your source voltage ends up being directly your input voltage. Otherwise, you're going to have an attenuated version of that source voltage driving your gate, and that's inefficient. Okay, and usually, since the logic gate you have is driving another logic gate, you'd also like to have a zero output resistance, which then becomes as if this was the source resistance driving another gate. So if you have these two things, it makes it very easy to drive other logic gates like yourself, and it becomes very easy to be driven. Like you basically are using all the supply voltage. So all these things and this shape make for an ideal logic gate. You're just as efficient, you're using the supplies as efficiently as possible. You're able to drive a lot of other gates without, wasting anything. So that's an ideal gate. Now, a bunch of the old technologies, so there was other logic technologies came before CMOS, and a lot of them, their transfer curves were far different than that. So here's a typical transfer curve. I'm not sure what this is. I'm going to guess it's on some kind of a pseudo NMOS logic gate. And you can see here's the input versus output. So similar to that previous one. It has roughly this shape of it has a shape of an inverter. So for a high input gives you low output, and a low input gives a high output. But let's talk about all the stuff that's wrong with it. So in this case, it looks like the supply voltage is 5 volts. So this is a very old logic family, just you can tell by the voltage. Okay, so let's look at what happens. So when your input is at 5 volts, your output is at 0.5 volts, roughly. So there's already bad news there, is that this becomes your logic low, your minimum logic low, which is not ground. So you lost half a volt of your supply voltage on the low side, which made you half a volt more susceptible to noise. And then when we look at here, when you look at a low input value, instead of using my high output value, instead of using the entire supply voltage, I'm at, 3.8 volts. Okay, so here also it's unequal to the logic high is unequal to the supply voltage. So I've lost 1.2 volts here so I lost 1.2 volts here. I lost on the high side. I lost 0.5 volts on the low side. Overall, from a 5 volt supply, I have lost 1.7 volts from the get-go. So that's 1.7 volts less noise margin than I could have had. So already, it's a bad situation there. Second thing that's pretty bad is that the slope is anything but abrupt. So remember, this is what we'd love to see. But instead, we have this really, low gain slope, say, between high and low. So what are all the bad things it can do for you? Well, if your input, has noise here, this guy will just kind of be sitting close to your output, and the output is also going to be going up and down. So it's more like, it's sort of almost gaining up your noise. It's not rejecting your noise. It's really gaining up your noise at these levels. Okay. And the other thing it's doing is, notice because of this fact that we don't have this abrupt thing, so we just it basically pushes the noise margin, makes it a very, very small. So this is the sort of close to the highest value of one we could get. And then the lowest value of a one we could get would be sort of around here. So it's really making the noise margin very, very tiny. We'd like to have the noise margin be half the supply. But in fact, it's like, I don't know what it is, a tenth of the supply or something. The noise margin high is a little bit better, but it's still kind of the same situation. It's only about a volt out of, instead of 2.5 volts, is a volt. So this is an example of what things look like before CMOS. If I did the same thing for you guys with a CMOS inverter, it would look something like this. So it won't quite have the exact sharp response, but it'll be very close to it. So this is one of the things that made CMOS really attractive over the what was previously available, which was a bunch of like NMOS logic families, etc. And so it was a huge improvement in reliability and noise margin. Okay, and anyway, this has like lots of other benefits that you'll probably see. I'm thinking about our lab one being designing an old time inverter, just to have you guys see what a crappy thing it is and how many problems it has, especially when you try to put a lot of them in the same circuit. Okay, so that's where we are. This is all the stuff with what an ideal transfer function would look like, and a less than ideal one. And so now remember, in this, by the way, in this lecture, we're still doing an overview, defining stuff, and we're going to drill down into each one of these later. So that was that. Then I'd like to also introduce you guys. We'll be talking about, so one of them is, so we've been talking about robustness. That was all transfer function, noise margin, all that stuff. The second thing we said was important is how fast the circuit runs. Okay, and so to define that, we're going to have some definitions of a delay. Okay, so this looks like these two curves. Now, instead of the input voltage on this horizontal axis, we have time, but the vertical axis is voltage. But in one case, it's the input voltage, and in this input voltage, and this is the output voltage. So what does this look like? Again, this is an inverter. This is V in. This is V out. The output is an inverted version of the input. So if the input's going from low to high to low, the output goes from high to low to high. But it does it with a certain delay, because there's a certain delay from the input to the output. Okay, and we're going to define that. So the maximum value of delay is called propagation delay. So this is this propagation delay. And the propagation delay isn't guaranteed to be the same for a low to, this is the propagation delay. Whenever people talk about propagation delay, the naming convention is what the output is doing. So here, the output is going from high to low. So the prop delay here is called TP for prop delay, high to low. Okay, so that is not guaranteed to be the same as when the output is going from low to high. That's called prop delay, low to high. Okay, prop delay, propagation delay, is always defined as input at 50% transition to output at 50% transition. So what does that mean? It means you start measuring your prop delay when the input is at its 50% point. Notice this is 0 input, this is the 1 input, this is 0, this is the supply voltage. So here's when the input is at its 50% point. You put your cursor here and you look at the output when the output gets to its 50% transition point, and this delay ends up being the high to low propagation delay. the amount of time it takes a 0 on the input to get the output to go, sorry, the amount of time a high value on the input, a high going transition on the input creates a low going transition on the output. And same with the low to high prop delay. Okay, so that's propagation delay. There's another component of speed called the rise and or fall time. Again, you have there is when the output is going low, you got the fall time. So there's a finite amount. So that's talking about 50% to 50% point. That was a prop delay. But also when you go from a legitimate high voltage to a legitimate low voltage, there's a certain amount of time that takes, and that's called rise fall time. And that's always defined as the 10% to 90% point of your supply. Okay, so it's the time it goes, the output goes, so this is a fall time. So it's the amount of time the output goes from 90% of its highest value to 10% of its highest value. And then the rise fall is vice versa, 10% to 90%. So those are those delay definitions. And again, we'll come back to this and look at this a lot harder and what you can do to design around it. What I want to talk about this, I think I'll leave this one and come back to it later because it's not really going to make sense now. Well, let me. The only thing I'll say about it is when you are doing a hand delay calculations, there's delay simulations you do in Spice. This is what you'll be doing in the lab, in your CAD tools, etc. But it's a lot of this class will be about how to do first order sort of hand calculation or hand estimation of things like delay and power consumption and stuff like that. And the reason for that is the simulations are really useful once you've decided this is exactly the circuit I want to build, and then you sort of capture it and simulate it. The problem is that's kind of putting the cart before the horse. You don't know if usually the way things work is your customer or your management or the marketplace is giving you a specification for how fast your circuit needs to be to do a particular function. Now, if you design your circuit and then you find out it's not fast enough after you do the simulations, you're already well into your project schedule. Then at that point, you're kind of going to take a big hit to go redesign your circuit to get to the right speed requirement. So it's always helpful to have these techniques to quickly analyze your circuit to decide if it's roughly fast enough. Are you kind of on the right track? And so right up front, to that way you can make sure that you'll be pretty successful when you get down to simulating it. But you just won't be completely off the right track. Same with power consumption, etc. If you can do some back of the envelope calculations, you will basically allow you to architect your design up front and not lose a lot of time going into the wrong path and having to come back and redo a bunch of work. So one thing we do when we analyze these gates is we do like extremely simplistic assumptions to make them look like a simple RC network. Okay, and we'll see how that's done, but it always ends up being like a first order RC network just to do a quick calculation. So, when this is sort of And it's like a reasonably accurate model of how an inverter works. And we'll see why that is and what the typical values are. How do you calculate the values for R and a C in a particular process? So I'll just leave it at that. And anyway, we'll look at the exponential behavior, et cetera. Okay, so that's sort of what we talked about speed. The other thing we talked about was power consumption. Okay, and power consumption has a bunch of different definitions. So because of the way CMOS logic works, it has a certain power consumption when it's switching and a certain power consumption when it's sitting idle. Okay, so these are different power consumptions. So what does that mean? That means if you're talking about power, you end up with a bunch of different definition of power. First one is an instantaneous power. So if I was gonna plot somehow time and power, what you'll see is there'll be high and low values for power, because at any moment in time, some of your gates are switching and some of them aren't switching. And so if I look at any particular slice of time, I'll get a different power value. And that's this instantaneous power, which is a function of time. And because the definition of power is voltage times current, the voltage is always the supply voltage. So it ends up being the instantaneous power ends up being supply voltage times the instantaneous current at that point. So sometimes you're drawing a average current, sometimes you're drawing a low current, sometimes you're drawing a high current. So the instantaneous power is always sort of moving up and down. Okay, so if you have this varying power, there by definition is a point where you'll get the maximum power. So that's called the peak power. And that's also an important factor, as we'll see, because it'll define certain things about your packaging, et cetera. And again, that's the supply voltage times the maximum current, okay? So if your instantaneous power is changing, you also have something called an average power. You could take a period of time here. Let's say it's an hour, or it's a period of time where your cell phone is in talk mode, or a period of time when your cell phone is in sleep mode, whatever period of time you want to figure out the average power of. And then you can integrate the instantaneous power, okay, during that period. So you take your instantaneous power, you integrate it over that period, and you divide it, because you want an average power, you divide it over that period you integrate it over. Okay, and you end up getting something like that. So all of those things are important, and you end up with them because you don't have, the power does not stay the same with time and with function in your chip. So whenever you read about, or the power consumption of this chip is 11 watts in certain operating mode, et cetera, it's talking about the average power consumption over that operating mode. Okay, it's 11 watts, 40 watts, whatever it is. Okay, so that's power dissipation. Again, we'll talk about that in detail. Energy is important. We'll talk about energy because we're talking about using mobile type devices, etc. So that's sort of, you're pulling energy out of your battery, and it's something you need to worry about. And then we're talking about the first order RC network. We're going to come back to this in a bit. Okay, let's see. I had a question here from, let me see, what is the chat? Yes. So Danush asks, do we assume that the supply voltage is constant in this sort of when you calculate power? Yeah, you do. You assume it's constant, which is kind of a iffy assumption for reasons that you'll see. But anyway, we can't change everything at the same time. Okay, so that was the introduction of the class. Now we're gonna go to talk about how do you sort of, again, this is introduction. We talked about the figures of merit, which was robustness, which were costs, which were non-recurring engineering and cost per part. It was reliability, which talked about noise margins. It was speed, we talked about prop delay, rise fall times, and it was power consumption. So again, we're gonna hit on all those things separately and in much greater depth. So now, as a next step, what I wanna talk to you guys about is how do you actually build a wafer or a silicon part? And what does it look like? Okay. And that's always like super difficult to do, especially, online, etc. So what I did was I'm going to show you guys a couple of videos and kind of like start and stop the video, maybe talk about it here and there a little bit. They're really short videos, and a couple other things before we jump into slide deck 3. Okay, so I have the link to all those videos and stuff, so you can also watch them later. But let's see if I can get this. This is going to get pretty hairy. Okay, let's see if I can do this without. So when you're viewing, I share screen. Okay. Okay, so hopefully everything will come through, including the audio. I mentioned this I think in the first lecture, is that the people making semiconductors now, we have two primary vendors, two primary companies selling that. The one that really sort of almost made the industry is called TSMC, stands for Taiwan Semiconductor Manufacturing Corporation, and it's in Taiwan, or the majority of the plants are in Taiwan. And so this is a video from BBC talking about that company. Okay, so hopefully it's
30 years, Taiwan underwent mass.
Did you guys every audio is coming through and everything?
Yeah.
Okay.
Yes.
Okay. Great. Okay.
Industrialization in what has become known as the Taiwan miracle. Huge tech firms grew, becoming household names. Asus, HTC, Acer. At the center of this was the semiconductor industry, led by a company you've probably never heard of, TSMC. It's one of the largest semiconductor manufacturers in the world, producing the chips inside some of the best phones, including the iPhone 11.
It is most likely if you have a smartphone, you have something made by TSMC.
And these chips were only made possible thanks to the discovery of semiconductors.
Why is semiconductor important or interesting? Because it changes your life.
With factories, or fabs as they are known, across the globe,
Okay, so let me describe this to you guys. So when you go into a semiconductor factory these days, these are, like I mentioned, these are extremely expensive manufacturing plants, multi-billion dollars. And physically they're sort of big places, but there's very few people actually working in them. And that's because part of it is that, we're talking about 3 nanometer, 5 nanometer lines, et cetera. And you can imagine what just a single particle of dirt, or something that's a couple of even micrometers, if it lands on a wafer while it's being processed. So everything is actually done robotically. These boxes, I don't know if you see my cursor or not, are sort of floating around on these rails. They go to the appropriate piece of equipment. Those wafers get put into that piece of equipment. It all happens under vacuum. So the stuff in these boxes in vacuum, the equipment's chamber is in a vacuum. They kiss up with each other. So both under vacuum, they open up, the wafers get shifted over under vacuum. So everything's constantly in a vacuum, and people are really good generators of particulates. So you want them away from everything. And so that's why you see all these things moving around without a lot of people being involved. Okay, let's go back.
Just is here in Taiwan. And we've been granted exclusive access to see just how those chips that form the heart of our electronic devices are created. But before we could go into the fab, there was quite a process to undergo. I have to take my shoes off on the carpet. I put them in a locker, it seems. And that was just the start. I had to put on a hairnet, wash my hand, and wear this to keep the dust out. Phew. But it is time for an air shower. Weird, I feel like I'm in the tumble dryer.
The manufacturing of wafers has to be extremely precise. They cannot tolerate any particles that may fall onto the wafer and damage the chips.
So finally we were allowed in the factory, and there was a good reason for all of that faff. The speed of these chips relies on how many transistors you can cram into a tiny space. And when I say tiny, I'm talking nanometers. So even specks of dust would matter.
I don't really know how to describe how fine that 5 nanometer or 7 nanometer is. But I think people very often say, if you look at 28 nanometer, it was like 1/1000th of the diameter of a human hair.
In this fully automated factory, the lights are kept yellow to protect the product.
So as we'll see in the lecture, these multi-layers that are printed on the silicon, they get formed or they get patterned by a photolithography process. And the things that get put on the silicon that are sort of the layers that get exposed to serve as the masks, they're sensitive to light. So light of different wavelengths make them set. And if you had sort of a normal white light in this factory, you could kind of end up setting those in a wrong way. So this is like typical, you go in the fabrication facility, if you spend a lot of time in there, it gets really annoying, but they have this really narrow yellow filter light all the time on because they don't want to screw up this photolithography process.
Machinery is moving all around, but there are quite a few things in here we're not allowed to film because this is seriously cutting-edge technology, so it needs to remain pretty secret.
We have to protect our customers' information, whichever way we can. And so basically, we do not allow cameras to freely roam inside our fabs because inevitably they may pick up customer information.
Between all the automated devices in this facility, they travel 400,000 kilometers a day. To put that into context, that's 10 times around Earth. All of this is about the concept of keeping up.
So you guys see, so that was the sort of stuff moving around. This is picture of gas lines. So a lot of the steps in silicon manufacturing, they involve doping silicon or depositing different, like sort of depositing silicon dioxide or different like aluminum, all that stuff. And a lot of that is sort of gas. You have a lot of gases going around. So you have a lot of like pure gases as supplies for wafer manufacturing in a plant.
Moore's law, as predicted by Intel engineer Gordon Moore in the 60s. It refers to the doubling of transistors on a chip every 2 years, whilst the cost is halved. A concept increasingly hard to keep up with, despite us expecting a lot more from our ever-connected lives.
The next driver is what we call ubiquitous computing. It is computation everywhere at any time. All the devices are connected. Billions and billions of edge devices that are smart, that can compute at any time and communicate and link. And that will be the future enabled by semiconductors.
Okay. Oops. We can stop now. Okay. Okay, so that was one video. And then I was gonna, let me see if I can pop up. Give me 1 second, guys. Got this two-factor ident. Still working on it, guys. So I'm gonna be popping up over to Blackboard. Okay, let's see if I can open this. Okay, so new share. Okay, that one. Okay, you guys should be seeing something that says Wall Street Journal. Do you guys see that? Wall Street Journal, TSMC.
Yep.
Yep. Okay, so this is an article. I think by the way, regardless of whether you guys are interested in investing or not or whatever, Wall Street Journal is a great newspaper. I don't know if you get access to it over the Cal Poly. It's a little expensive to get. I think it ends up being like $40 a month, and then they have introductory offers. But anyway, great stuff, both on investing, but also they got a lot of good technology, business news. And so, just as an aside, there's other stuff that's specific for semiconductors and so on, but this is just a great newspaper. Start reading it today. Do yourself a favor. Okay, so I wanted to show you guys this article about. This is $28 billion. I think this is their funding that TSMC, which is the same company that we just talked about, is investing is just R&D for 2021. So this sort of gives you an indication of how much money goes into building these advanced factories and so on. So it's a very money intensive process, and you can see this is CapEx, stands for capital expenditure, is 47% higher than 2020. Sort of gives you an idea of the growth that this TSMC company is doing. And it's sort of like a really good article, and there's lots of other articles about semiconductors, but I just wanted to show you guys this as an example. Okay, so the next one, there was another video, and bear with me guys, once we're just gonna have a few more days before we go into the lecture, but it's this part about manufacturing the silicon is really hard to sort of explain, especially remotely looking at slides. So I thought this would give you guys hopefully some visuals. Okay, so we're back on to YouTube. Okay, do you guys see a bunch of the sand to silicon?
Yeah.
Okay. This is a similar video from Intel though, but it gives you a little bit more visual on the steps. So what happens is they make silicon, the actual starting wafer, starts from a molten batch of very pure silicon. And they basically, there's a method, I can never pronounce it, it's got a Chivuk's method, I don't know what it is. But anyway, they start pulling it slowly from a point up, and this happens over the matter of many days. And so you end up with this sort of a cylinder that, let's say if you have we talked about a 12-inch wafer, et cetera, that's like 12 inches wide, and then they're just pulling it up, and the silicon is solidifying as you're slowly putting it up all of this pure molten batch. So you end up with this kind of giant silicon salami bologna kind of thing. And basically you dice it through to get the wafers that then you're going to start using as your material. And you can make those wafers very thin because, as you'll see, the useful part of your circuits are just sitting within the very top 10 micrometers of silicon. Everything's sitting at the very top. And so the more thinner you can make these wafers, the more you can get per batch of this silicon tube, and the cheaper your starting material is going to be. But unfortunately, silicon also can shatter. It's not like steel or something. So you can't make it too thin. So almost all the time, the wafers that you end up with ends up being sort of about a millimeter thick, usually 750 microns. I don't know why 750 micrometers. And that's just to give it enough mechanical rigidity that you can handle it and it just won't shatter in your hand. So this is a cartoon of this lithography process we're talking about. It's called step and repeat, meaning that, you know, you have, I don't know if you can see my cursor, but you have a mask, and then that gets basically imaged to your wafer, and you're taking steps across your wafer, and you're exposing that mask to basically print these patterns on your wafer. Okay, guys. So, so those were the two videos I wanted to show you. And any questions about those, by the way? Okay, so the next thing I wanted to show you was, so it's, you know, I'm just trying to give you guys like visuals of what this stuff looks like. I mean, it's pretty clear in my head because I was working on this stuff. But so it's, you know, it's kind of hard to visualize, you know, when you, so that's how the wafers get made at the factory and sort of some steps. Again, we're going to go through the steps in some detail. But, you know, thinking about what actually gets printed is difficult to communicate and visualize. So especially when you're talking about a multi-billion transistor chip. So so I, you know, it's easier to show you guys something that's older, many generations older, and has a lot fewer transistors per chip. And I've managed to find that courtesy of one of your colleagues, Brendan Barros. So he was taking the class last semester, and he gave me to this link to these crazy people. And let me, where do I have those guys? Let me then share this other screen. This is like really cool to me anyway. Let's see, down here. So, how do I do this? So now I want to share the screen. Okay, so now we should be seeing something called, I guess seeing something called visualizing a classic CPU.
No, we're still on your Mac.
No? Okay, so let me do it another way. How do I thought it was sharing. How do I stop sharing? Stop. Did I start? Okay. Okay, so this is pretty cool because some crazy bunch of people, what they did was they went back and sort of reverse engineered an older chip, and they've done this for a bunch of other chips, and sort of shown what it looks like. Because this is kind of, you know, I don't know how many transistors in this chip, and this talks about it, but you know, we're talking about maybe 10,000 transistors. So, so the 6502 chip was what this actually talks about a little bit. So this 6502 chip was released, you know, about 40 some odd years ago. Okay, and the reason again that people looking at it is for fun, historic reasons, but I'm showing it to you guys just because it's a simple chip and you can kind of almost see what's going on in it to some, you know, not really, but you know, it's easier to get your head around. And so this was 40 years ago. The reason these guys are looking at it is because it's going down memory lane. It was used in the Apple, very, you know, Apple I, Apple II. I don't know if you guys know what, this is just the very first computers that Apple made, and some of the other cool Commodore PET. I used that when I was a kid, and Ataris, and sort of historically, it's sort of a chip. And again, it's used by sort of, you see these guys, Steve Wozniak, Steve Jobs. I don't know if you know who these guys are, but sort of going down memory lane. So this was the 6502 chip. Let's see, talking about his, you know, when he was a young guy, chip design. Okay, this is just talking about, you know, don't worry about this. This is how they used to actually, they'd have to draw these mask layers by hand, which is just absolutely frightening. But okay, so this was the chip. Okay, so this makes it a lot easier to get your head around. Only 3,500 transistors, and so it's sort of easier to think about. There were other sort of things they did here, looking at the schematics, but okay, so this was in a 8-micron process back in 1975. 8 micron. Okay, now we're talking about 7 nanometer. Okay, so that's, what is that? It's like 1,000 times smaller in a linear domain. Okay, so the nice thing is, but you can still see stuff in a microscope in an 8-micron process. So here is like a microscope picture of what things look like. Okay, and so you actually see these layers that are either built or etched on to silicon. Okay, and this shows that they extracted the layout. So this is what you actually draw. So usually what happens is you draw this and you send this to the foundry and they make this. They took this and extracted this. So anyway, it gives you an idea of what, when you draw a circuit, so you have, when you're designing a chip, you work in a couple of different domains. You draw the schematics, and the schematics look like, what we talked about. They look like an inverter in your schematic or a NAND gate, etc. But the fabrication facility doesn't know what this schematic symbol is. So you actually have to draw the mask that creates this, and it kind of looks like this. So this is looking down on the chip, and each one of these colors is a different layer, and they're all sort of sitting on top of each other, and then make the transistors, and then make the interconnections between these devices. Okay, let's talk about how it's delaminated. Taking images. Okay, so this is the picture of the overall chip. And I think I read somewhere, again, this is an older process, only 3,500 devices in it, but because it's an older process, it's already a pretty big chip. So this might be about 4 millimeters, I think, on the side, something like that. Okay, so the actual chip. And then if you if you're looking at it, it looks like a sort of a Persian carpet, or I don't know, whatever visual you guys want to put in, but you actually see like circuit structures, and these tiny things are, individual gates and transistors. So, so this is how you look at it. So when you're looking at the top down, so again, this is a picture. There are these layers that define different aspects of a transistor or different aspects of interconnection, and they're sort of sitting on, overlapping with each other. So these might be metal lines connecting different transistors, but they're drawn over these layers that define the transistors. Okay, and there are these different chip layers. There are so-called, these are very different than, I can only guess at some of these things because, again, it's a very old process, but some of the names are, of course, familiar. So vias, anytime you have a connection between two metal layers, it's called via. Contacts, or connection between a metal interconnection layer and a transistor. These are like metal layers that are making the interconnections, etc. So this is how they sort of built it up. So this is all, this PDF is in your in Blackboard, and you can sort of go on this website and see they've got pictures of just different layers. They've sort of individual layers, okay, which is kind of nice. And finally, let me show something that's the coolest thing about this whole thing is let's see if I can find it. Nope. Give me 1 second, guys. Ah, good. Okay. Let me go back to sharing my screen. Ah. Okay, now you guys see something says images of 6502.
Yes.
So you can see all this is like, again, the website that they have stuff. It's showing the pictures of all like the metal layers, the connections between the metal layers. You see those are just dots because they're only where the metal layers are overlapping and you want to get a connection between them. So on and so forth. But the coolest part of this, which I thought would be amusing, is this thing called, what they have called a visual simulation. This is going to work. Let's hope so. Okay, so what they did is, what they're doing is they're going through the microcode. So this is the microcode running something through this chip. And the different points in the circuit that are going high and low, you know, the ones and zeros bits going through this are lighting up and turning off as this thing is walking, this simulation is walking through the microcode. So this is the chip. These big pads here are points that, you know, you have these wire bonds that you make connections to the outside. So all this stuff on the periphery is sort of talking to the outside. So you see as signals are coming into the chip from the outside, these big pads are lighting up and off. And then it's kind of moving quickly, but it's kind of neat. You can see that the different parts of the circuit, they're like ones and zeros, are moving through this as you're stepping through the microcode. And anyway, things are running here. It's pretty unique. I think it's a cool way to kind of, it's really, again, really hard to visualize a chip, but I thought this was kind of a good way. So hopefully you guys can play with this and see what things look like. Okay, so now let's get back to the business at hand. So we're off to slide deck 3. So I'm going to talk about, you know, we don't have that much time left, but I thought this was a useful expenditure of time to get your head. It's just hard to imagine. So, but let me just sort of touch on a couple of things. Let's see, let me go back to. So I'm going to stop sharing and let me. Okay, so this is starting slide 3. So when everything we've looked at so far today was looking, so if you have a sort of a silicon wafer, so let's say this, I don't know, whatever, 12-inch in diameter, and then it's got a bunch of chips printed on it, and you know the whole thing is just printed screens. So we've been looking at it from the top down, which is, if I look at a silicon wafer from the top down, looks like a circle, and you know you're talking about inches and millimeters and stuff. Okay, so now if I take that wafer and look at it edgewise, and then, cut across it edgewise is what this looks like. Okay, so now this is the substrate. Again, looked at edgewise. So this will be, if I look at this, the real width of this will be, like I mentioned, 750 microns, let's say a millimeter thick. Okay, and basically all the transistors are sitting at the very top of this. So all the transistors are sitting at sort of the top 5 to 10 micron of the silicon. And then on top of that, you grow your polysilicon gate, oxide, dielectrics, etc. Okay, and so this is what they kind of look like. You have, this is a, so this is supposed to look like an actual, what things would actually look like. This is an NMOS transistor. This is a PMOS transistor. So you know that because you have N plus for the source drain. So again, if you guys don't remember the transistors, you might want to refresh yourselves. But so it's basically end up with N's for the source and drain of an NMOS transistor. So source drain or drain source are symmetric. You have the gate, okay, here, and you have the gate oxide, and we'll talk about, we'll do kind of a refresh on a transistor, sort of, I think, in the next set of slides after this. But anyway, so that's what it looks like as an NMOS. A PMOS transistor looks very similar, except it's kind of switched. Source and drains are P plus, and it has to sit in an N well because the channel is N type for a PMOS transistor, and a channel is P type. This should be a P. It's kind of got, whoops. It's kind of got a bit off here. So it's a P minus, P plus, P plus. Okay. Okay, so then we're going to talk about all sort of some examples and the steps. You saw the videos as it was like these wafers were going through and you're building up these different layers and using lithography. So we'll go through some of these steps and show how by superimposing all these different steps, you will actually end up with something like this, which is a wafer with a bunch of transistors sitting on the top of the layer, and then we'll see a bunch of interconnections that are sitting on top of that. Okay, so with that, guys, I'll stop here. Any questions?
Professor, I had a quick question.
Yeah.
It's from your sand to silicon video that you showed. I think they depicted the wafer being cut with blades.
Yeah.
And that's how the different chips are being separated.
Yeah.
Is that still the current process? Because it seems a little archaic.
It's archaic, but it's still the process, man. It's still, that's how it's done. They get these, you'll see if you go to the assembly, what they call the assembly place, you'll see the wafer, it's squirting water on it, and there are these saws cutting through it. I mean, the saw blades are precise, but still, if you look at it under the microscope, it looks ugly as hell, man. There's like chips flying everywhere. It's kind of a dirty process. So what you have to do is when you lay out these dies in your wafer next to each other, you actually build channels for that saw to go through. So one, you make sure that there's enough space between these different die in your wafer that you can cut through. And then you surround your chips with something called a seal ring, as in like sealing something, to make sure that these cracks and things from the sawing process won't propagate into your chips. So you build a bunch of moats around your chips to kind of make up for the sawing process. People, so we have customers that use a laser cutting process. So that's sort of what you and I would expect to be happening in 2021, laser lines, sort of cutting very precise cuts, etc. But it just ends up being more expensive. So like this particular customer is in the medical space. They don't want any kind of size is very important to them. It's because it goes into a hole in your body. You don't want it to be too big. So they don't want any excess silicon from the cuts, etc. So they use a laser process to get a very precise cut. But again, that's an expensive chip that they're putting together, and it's going into $1 million sort of surgical piece of equipment. Sort of regular chips, yeah, still saws and dirt and crap. I mean, by dirt, they're still very clean, but fundamentally, it's just a saw cutting through silicon.
Do they use water jet cutters by any chance, or is the water too wide? Like a water jet cutter, like.
They might. I haven't seen that. I've either seen saws or lasers, but they might be using water jet cutters somewhere.
Okay, I was just curious. Thank you.
Yeah, sure. Anything else, guys? Okay, if not, I'll let you guys go. Just one more note. Sometime between now and Thursday, I'm putting your first lab online, and it'll be around sort of designing crummy old-time NMOS inverter. And as part of that exercise, I'm hoping you'll see all the bad things that those older technologies have, and sort of by comparison, how nice as we get to CMOS technology, how much better it is. Okay, guys, have a good night and see you guys on Thursday. Take care. Bye.
Have a good one, Professor.
Thank you. Take care. Bye.